Identify the major type of intermolecular forces between particles of each of the following compounds. So when we think about intermolecular forces, we're thinking about things like ionic bonds, hydrogen bonding, dipole-dipole attractions, or dispersion forces. We're going to decide which of those four applies to each of these different compounds. Okay, and so let's go through them one at a time and think about that. This first one here, magnesium fluoride, MgF2, we want to think about, like, what does this thing look like? In the most basic sense, we can look at what atoms make up this compound and see that magnesium is a metal and fluoride is a non-metal. So what is that going to tell us? If we have a metal plus a non-metal, that means that this thing is an ionic compound. If it's an ionic compound, it's going to have one specific type of intermolecular forces. It's going to have ionic bonds. It's oftentimes the easiest to see which things will have ionic bonds because they're going to fit this pattern. Ionic compounds have ionic bonds, and to be an ionic compound, you have metals combined with nonmetals. So that's it for the first one. Okay. Second one's going to be a little more involved. We want to look at this and think about its structure. Okay. You may go through a Lewis structure. You may draw the shape. If I go through and draw what the shape of this molecule looks like, right? This is what ammonia looks like, NH3. Okay. When we look at this structure then, we want to think about the various criteria for the different types of intermolecular forces. Okay. What I've got here fits one of those criteria perfectly. Notice here I've got hydrogen that's directly bonded to F, O, or N. In this case it's N. So I have H bonded to one of those three. And I also have a lone pair on F, O, or N right here. It's a lone pair on N. If I have these two criteria, I result in a special type of strong dipole-dipole attraction called hydrogen bonding. Remember, hydrogen bonding does not mean literal covalent bonds with hydrogen. It's a name of an intermolecular force. That's a strong type of dipole-dipole. It's a special thing. When you have these two types of criteria satisfied, that's when you get hydrogen bonding, like here. Okay, let's look at CH4. If we look at the structure of this, it's tetrahedral. I've got 4 CH bonds. These 4 CH bonds, we need to think about if they're polar or not. Turns out CH bonds are nonpolar. They have an electronegativity difference of 0.4. Okay, and so we have all nonpolar bonds. That means that the molecule is going to be a nonpolar molecule. If I have a nonpolar molecule, there's only one type of intermolecular forces I can have. Those are dispersion forces. Remember, dispersion forces arise from temporary, instantaneous dipoles that form in nonpolar molecules, and that's why they're the weakest types of intermolecular forces. Okay, all right, let's squeeze this last one over here on the right. CH3Cl has a structure that we can draw something like this. Again, it's going to be tetrahedral with carbon in the middle. Okay, and now I've got two different kinds of bonds. I've got a CH bond and I've got a CCl bond. We know that CH bonds are nonpolar, so they don't have dipole arrows. We can look at the CCl bond and see that this is actually a polar bond. And look at the electronegativity difference, and it's greater than 0.4. It's going to have a dipole arrow that points towards the more the more electronegative element, which is chlorine. So I'm going to have a dipole arrow right like this. That means that this is a polar molecule, right? If it's a polar molecule, and it doesn't fit one of these special criteria, right? I don't have hydrogen bonded to FON here. That means there's only one thing it can be. It can be dipole-dipole attractions. So these problems can be difficult because what you need to be able to do is decide if your molecule is polar or not, and look even a little more deeply at the structure of the molecule to figure out which of the intermolecular forces are involved.